Okay, welcome back to Fluid Mechanics. This is material for Class 4, and this is video 2 in Class 4. If you haven't already, check out video 1 for the background where we develop, or at least we introduce the equations that we're going to use here. All right, so let's see that here's the example, and this is an example. This is problem 297 out of Munson. And we have a 4-foot wide gate, so that's the dimension that's out of the plane, and it pivots about a frictionless hinge right here, and it has this like counterweight that weighs 2,000 pounds right here. And that's located, it's got like a little bend in it, so it's like 3 feet, and this is 2 feet right in there. And what we want to determine the depth of the water if this thing is being held in place in this manner. So I'm going to draw 2 free body diagrams. One of the very most important things to have in your mechanical engineering repertoire is to be a really good free body diagram drawer. So my first one is just going to be representative here of what the scenario is, right? So these are going to be like sort of equivalent type of things right here. So here, let's see, am I on the page? Yes, I am. All right. And this, we're going to draw, this is the part right here where we're going to draw. We're going to isolate it. And right here is the hinge. And here's some weight coming down onto the thing. And I could either label this with a W or put the value in there, right? Maybe I'll put the value. So I'll go 2,000 pounds. And we have a pressure gradient that looks like this right here, right? So it's a triangular kind of shape right there. And that pressure is distributed right here along those lines. And then to be complete, we want to put the reaction forces right here. And they decided to call that point O. So I'm going to call my reaction is going to be rocks. And then there's one right here that's Roy. Right, so that's R subscript O with a Y in there, and I kind of had to draw that a little darker right there so you can see the arrow. Now that what we really want to do is find an equivalent FBD. So maybe I'll move the FBD just down a little bit right there. So an equivalent with equivalent loads coming into this. We'll put all these same things back in there. Right, with our 2,000 pounds. So come on, baby. There you go. Okay, so 2,000 pounds, and we're focusing. Yes, we are. Here is my rocks. And then here is Roy. And we're going to have a single force. It's not going to be at the center, right? It's not going to be at the center of the thing. It's going to be down somewhere. I'm going to go ahead, even though I could find this, just knowing that it's going to be 1/3 from the bottom. I'm going to go ahead and use the equations that we just introduced a moment ago, just to kind of show, where we were kind of how we're using them right there. So I'm going to write this FR right here, and I'm going to write this distance right here. I'm going to use the book's nomenclature and go YP. Right, so here's that equivalent force, and here's the distance it is from the top, and might as well put some other dimensions right on here. Let's we're going to take the sum of the moments about this point right here. So we're going to want a distance that's perpendicular to the line of action of the force. So even though they gave us that dimension, we actually don't need that dimension for anything. They were trying to be tricky with us, I think. So right there is our FBD. And what we want to do with this, and I'm going to use this space over here maybe for the sum of the moments about O is going to be equal to 0, right? So first one, we need to have this distance in between here and here, right? So that's going to be, this distance is going to be H, which is the total depth right here, minus the YP, right? So we'll say, and it's noteworthy, it's going counterclockwise, right? Because we're doing it about O, So this one's creating a counterclockwise moment. So that's going to be positive. Generally, that's what we use counterclockwise as positive. So we have FR, but it's going to be this distance right here. So it's going to be H minus YP, right? And then this, of course, these pass through the point about which we're taking the moment, so they don't count for anything. But this weight right here, it's going to go clockwise, right? You can see that that's going clockwise. So it's going to be negative, and it's 2,000, and its moment arm is 3, right? And it's going to be equal to 0 because there's no other forces going on here. So I'm just going to call that equation 1, and we're going to come back to it. Let's try, we need to find this value and this value. We can from the arrangement. This one's going to be, it's going to be also in terms of H. So we're going to be able to solve for H. That's our main goal, right? We're trying to find what the depth is that makes this thing balance. So first off, I'm going to find the value for FR. And I think that's going to have a term that has H in it, right? So remember that we had what we said. We said gamma YC times, let me see, let me double check. I said the sine, right? Let me see. They said the sine, sure did. Sine of theta times A, right? So that's the area of the thing. So FR is going to be equal. Now this is water, and we're using US units. So we're going to go 62.4 for gamma. That's cubic pounds per cubic foot, right? Well, I'm going to leave the units out right here, but we know that we're going to treat everything in feet. YC for this is just going to be 1/2 of H, right? So H over 2, right? So that's the location of the center of this rectangular gate, right? So this is a rectangular gate. So it's going to H over 2 and sine of 90, right? Because it's vertical. And then lastly, the A is going to be the width times the height. Well, we know the width is 4 feet, and we're trying to find H, right? So if you do with all this number, these things, we can condense it down into, because that becomes 1, and we get 124.8, and then H squared. Okay, so we've got FR. That's going to be, but it's in terms of H because we don't know that. It's the thing we're trying to find. Now, the next thing we want is YP, right? So YP is going to, the equation that we presented before was the moment of inertia about the x-axis, right? And divided by YC and A, and then we add YC back to it. Now we know that a rectangle is BH cubed over 12, and the H in this case is actually equal to H, right? It's going to be the height. It's the thing we don't know. So that's 1/12 base, which is the width in this case. So that's 4 times that H cubed. All right, divided by YC, which is we knew was H over 2, and divided by area, which we have is 4 was our width, and H is our height. I drew the H kind of funny. Okay. And then we also have to add this back into it. So that goes H over 2, right? That YC, right? With this, let's see, we do a little bit of manipulation and canceling out of things. And we're going to find that going to be equal to 2/3 H. So now we want to plug this and this back up into the equation that we had up above. So we're going to have FR of 124.8, and where we go? Yeah, H squared, right? I'll put brackets in here, and we're going to have H minus our YP, which is 2/3 of H. Oh, and by the way, maybe we should think about that. Noteworthy, we could have predicted that, right? We would known that it was going to be 1/3 from the bottom or 2/3 from the top, so that's what we've confirmed right here. We could just, from observation, we could have told that that was going to happen, but we're just demonstrating that we're using the equation. And then we need to subtract out that 2,000 times 3. set it equal to 0, right? And we do all of that, we're going to find that we have a depth. Well, no, actually, let's do it in stages here. This is going to be h cubed that we're going to find, and it's going to be h cubed equals 144.2. And these are going to be cubic feet, by the way, if you were to work the units out of the thing. And so taking the cube root of this, we get 5.244 feet. And I would like you to rewrite the answers out. And let's just give it in 3 sig figs. And say that we're done. And so that was the first example. Let's make another video.